Okay, here's where we start packaging things together, okay? We start getting factual statements that we are going to use. So far we have definitions, and that's great. We have some basic vocabulary and their meaning, and we will absolutely use those. But now we're going to start coming to some common agreements about things we can't prove, okay? And then we're going to start packaging up proofs, and we're going to talk about that. So big ideas. Postulates are just assumptions, okay? We try and have as few as possible, and we try and only make really obvious, unprovable things agreed by all. That is a postulate. We all agree. We want as few as possible, maybe like 10. I mean, in this class, so we won't go into crazy detail. We'll have more like, I don't know, 20 or 30. But Euclid's elements, classically, like to build geometry, he tried to keep it to like 5 or 9. And there's big mathematical arguments over whether certain axioms or postulates were really needed and whether you could prove them using other ones. And trying to keep it with as few assumptions as you can, and then to build all of geometry, that's the beauty. Okay, so a postulate is just an assumption that we all agree is true, but we can't prove it. Okay, kind of like those 3 undefined terms, point, line, plane, and then we build from there. Okay, we can combine these postulates with old, definitions and past things we've proven and deductive reasoning to make our first proofs. And that's what the next 2 videos will be about. Algebraic proofs, geometric proofs. Oh, actually next 3 videos. And then even proofs about angles too. Okay. And then when we package up a proof, we call it a theorem. That way we don't repeat the same steps again. We just give it a nickname. Okay. And we'll get into that. All right. So a postulate, again, is an assumption we all agree to make together, because it seems so obviously true, but we can't prove it. Like the first postulate we do, through any 2 points in space, there exists exactly one line. Can't prove that. Okay, we could do some, now if you do, what's it called, indirect proof, you could say, well, let's assume that there are 2 lines that pass through the same, and there are methods of doing it. For this class and the scope of this class, we're going to call that a postulate. Through any 2 points, there's exactly one line. Seems super obvious. We're all going to agree that that's true. Okay, postulate 2.2, our second one, is through any 3 points, and they're not on the same line. So these are 3 non-collinear points. There is exactly one plane. And these are going to be useful. Honestly, we're not really going to use these 2 in that many proofs, but it's giving you clear examples of the sorts of assumptions we make. They seem really obvious, and yet we either can't or we don't want to go through the rigor of creating large proofs, okay? All right. So here are the postulates. There's 7 of them that we have in this section. Okay, so 2.3 is kind of the reverse. We say if we start with a line, we could assume there's at least 2 points on there. Okay, we could put 2 dots on that line, and we could use those in a proof or a construction. Okay, 2.4 is kind of the opposite, or the of 2.2. It's saying if we have a plane, it contains at least 3 points. So you could put 3 points on there. Okay, and those 3 points are non-collinear. Okay, and then I won't read them all, but those are the assumptions we're making, okay? Now a theorem is simply us saying, okay, I proved steps 1 to 7, I proved this thing is true. And this is going to seem like I'm just talking and I don't have specific examples. That's because the next 3 videos are all about actual proofs, and we will see how we can then reuse them. So for example, if I do one proof, and this one proof is, like steps 1, 2, 3, 4, 5. Oh, I did it, right? So A led to B, B led to C, C led to D, D led to E, E led to F. So I just proved that A leads to F. Well, let's say we give that a cool nickname, okay? So this is going to be called Fire Eagle Theorem, okay? So we just give it any old name. Oh, good old Fire Eagle Theorem. I'm going to reuse that sucker. So then we come across this this other thing that we need to prove and go, oh gosh darn, we really need to show A leads to G. So if A is true, then G is true. And then we go, well, I already know that A leads to F. Okay, that's Fire Eagle Theorem, right? And then we go, oh, and because of this over here, well, F leads to G. So, oh my gosh, we just proved it. A leads to G. So rather than repeating all of these steps that we did to get from A to F, then just to get from F to G, instead, we say, I'm going to package this proof up. I'm just going to give it a nickname. That's it. All that nickname does is say, refer back to where I proved this, in those 5 steps and just copy and paste those 5 steps here. I don't want to repeat myself. So I shortened those 5 steps and gave it a nickname. But really it's saying do step 1, step 2, step 3, step 4, step 5, and then F to G, and all together that leads you from A to G. That's the whole idea of a theorem. It's just avoiding redundancy or repeating yourself. And that'll become really useful as we start to make our first useful theorem. One of the first ones we'll do is the vertical angle theorem, and we will use that one all the time. We don't want to reprove that every single time and have those like 5 to 7 steps in every single proof for the rest of the year. Instead, we collapse those 5 to 7 steps and we just say, we know these 2 angles are congruent by the vertical angle theorem. And we prove that, right? Those are steps that we made. We just package it up and give it a name. That's the idea of a theorem. Okay, so I'm going to save proofs for the next one. This book does 1 proof. They do the midpoint theorem. It's kind of silly how short it is. It's an alternate form of the midpoint definition depending on the book. So I'm going to skip that proof, okay? So the theorem is if M is the midpoint of AB, then it breaks the segment into 2 congruent parts. Whereas the definition technically says then AM equals MB. So depending on the book, the definition of the midpoint is either 2 equal segments or of length, or 2 congruent geometric object segments. So I thought that was just kind of a silly proof to go between the 2. So we're going to wait till the next video to really dive into proofs. So let's just do some problems to kind of practice. I mean, really all we have are these 7 postulates and the conceptual idea of what a theorem will be, okay? So let's dive into this, okay? Draw figures to illustrate postulates 2.6 and 2.7. So 2.6 says, if 2 lines intersect, then their intersection is exactly 1 point. So the if and the then is kind of hard to portray in a picture, but we can definitely draw a picture of 2 lines that intersect. So this is for 2. And so here's 2 lines that intersect, and they intersect in exactly 1 point, right? And then 2.7 says, if 2 planes intersect, then their intersection's a line, okay? So what we've got here is, I'm just going to draw a plane, okay? And then we have another plane that's going to hit right here, and maybe it comes out, I don't know, this direction, okay? So it's going to go like this. Now this is going to be behind. I'll fix the what's dashed and what's solid. Okay, so what's solid? This is solid. We can see this line. And then this little thing here, and I'm going to do, so here we go. This little part will be dashed. There we go. All right, so that's a drawing of where 2 planes intersect. And what do they intersect at? A line, right? That crease. It's kind of like the seam of a book, right? You open the 2 pages that are 2 planes and they meet at the crease or the seam of the book. Okay, so list the types of reasons that can be used for justification of proof. So this is kind of endless, right? But what are some? So for 3, what could we use for a proof? Well, definitions are going to be really helpful. We're going to use those all the time. Okay, so theorems, things we've proved in the past, we can absolutely use those. We can also use postulates. We all agree those to be true. Something that you may not think of is often we just use the given statement, right? That's going to be your starting point. That's going to be your law of detachment, the first fact that you're given that then leads you forward in a proof. So you've got to start with some kernel of knowledge, right, to move forward in many proofs of that style. We can do abstract theorems too, but often we'll just use the given to get started in a proof. What else? I mean, there's lots of other things. They have a list in the book. Let's see what else they say. Undefined terms, algebraic properties. So undefined terms, that's right, because there are no definitions. So that's a point, a line, and a plane. I don't know when you would ever say a point as the reason for a step, but you could use undefined terms in a proof, absolutely. And then also properties of equality. So in other words, we can use all of the algebra that we know. And that's what we're going to do next, because where do we start with proofs? We don't have that many terms. We don't have that many things in geometry that we can use that. We basically just have some level 1 like vocab, but we don't have a lot of things to combine yet. So what we're going to do to practice proofs is use something that we're familiar with, and that's in the next video. We're going to do algebraic proofs. So using algebra as a template or as a tool to practice proofs, okay? All right, so determine whether the following statement is always, sometimes, or never true. The intersection of three planes is two lines. Whew, it's a doozy. Okay, whoa, now we're talking about spatial reasoning with three planes. So this is one of the reasons I love geometry. Trying to just wrap your brain around the intersection of three planes is a healthy exercise. Just like going to the gym and doing push-ups is a tiring, uncomfortable feeling, I'm tired, I want to quit, feeling for your muscles, but then after that and some rest and recuperation, your muscles are stronger than before. It's the same thing with this. The more you're exercising that, how do I wrap my head around this uncomfortable thing, that's exercise for the brain. You're expanding your mind, making new connections. So let's think about this. Let's look at our postulate and that past picture, 2.7. So if two planes intersect, they intersect in a line. Okay, so that's really where this is coming from. Okay, so let's draw. We got two planes. Okay, and they intersect in this line that we just drew. Okay, so what does it look like then to add a third line in here? So think about this though, the intersection of three planes. That means the intersection is the points that lie on all three planes, right? That's what the intersection of two things is, right? If I say the intersection of two lines, I'm saying what points lie on both lines. So there's only that one point. So really the intersection of three planes is what points lie on all three planes. So the intersection of these first two is just a line. So really I could simplify this and say the intersection of a line and a third plane, right? Because two planes either don't intersect, or so I can say nothing, and a line, so we're either taking the intersection of two planes, which is a line, and then intersecting it with a third plane. Or the first two planes were parallel, like two sheets of paper in a book, like page 5 and page 105, right? They're parallel, they're never going to touch. Ignore the seam part there. And so either we've got two planes that don't intersect at all, or two planes that intersect in a line. I guess technically you have three. You could have two planes that are the same plane, and so they intersect in a plane. But usually when we say two planes or three planes, we're talking about two distinct, unique, separate planes. So that we're discluding the case where they're the exact same, because then everything gets redundant. We just have to add extra words to every problem, and they are not the same. Okay, so let's look at this. What is the intersection between a line and a third plane? Well, we got a couple options, right? So if we have the line and the plane cuts down kind of like this, and so boom, and then this becomes like dashed over here, well, we could have it be a point. Okay, so already this is false. Or we could have the plane and the line intersect like this, right? And so we could have the intersection be a line. Or we could have the plane and the line be parallel, and so there's nothing. So there's lots of options, but for sure it's not two lines, okay? But there's lots of ways to think about this. And wrapping your head around that, that's a healthy, beautiful exercise there. Okay, let's go to the next problem. So in the figure, it says those two lines are on the plane. So these lines are on the plane. And then it says W is on BD. Okay, yeah, that's clear in the picture. State the postulate or definition that can be used to show each. Okay, so B, D, and W are collinear. Those three are collinear. Oh, why, that's just the very definition of collinear, right? The definition of collinear is there exists a line that contains all 3 points. That's it. Okay, great. And so we see visually a line containing all 3 points. And so that's the very definition of collinear. So E, B, and R are coplanar. So we don't visually see a plane containing this 3. But how would we know that those 3 points are coplanar? Oh, it's a tough one. Well, we don't visually see a plane, so we can't just use the definition of coplanar. But do we know anything about 3 points? I mean, I told you in a video a while back that any 3 points are coplanar, but how do you know that? And we could go up to here, and we could go through any 3 points not on the same line. There is exactly one plane. So if we take these 3 points that are not on the same line, there exists exactly one plane that passes through them, and that's the very definition then of coplanar. So right here we would use postulate 2.2 saying there exists a plane. So if we were being really clear, we would say this would be the postulate 2.2, and then plus we also use the definition of coplanar. Right? So the postulate told us that there was a plane that went through all three. And then the definition said, since there's a plane going through all three, we now know they are the word coplanar. Okay? R and W are collinear. Oh, that's exactly analogous to the last one, except in a lower dimension. Rather than 3 points plane, it's 2 points one-dimensional line, but it's the same idea. We have 2 points. I don't even need to look at the picture. Any 2 points are collinear because, again, we go up to here to the first theorem, and we have through any 2 points. Doesn't matter anything about those 2 points. There exists exactly one line. So we go down here and we go, oh, well, that's exactly postulate 2.1, the very first one. Plus then, after we know that there is a line going through points R and W, then we also say, oh, well, that's the very definition of collinear, right? And I guess even if we really wanted to get specific, we do not need to get this specific, but even for 7, you could say, given that right here, this line and the image, and we could pull in a lot of information and then say it's the definition of collinear. Okay, well, I always leave off the last letter. That's silly. All right, so let's do a couple last problems here. So determine whether the statements are always, sometimes, or never true. I love these problems. Okay, 3 points determine a plane. Oh yeah, 3 points determine a plane, right? Not always, right? So determine means unambiguously choose one, and I could communicate that with someone else and we would both absolutely know we were talking about the same plane. So that's sometimes. And when does it not unambiguously choose a plane? It's only if non-collinear, right? Because if the 3 points are in a line, there's infinitely many planes going through it. There's this plane, there's that plane, there's that plane. There's so many planes that go through those 3 points, so it doesn't determine a plane. There are planes that go through those, so they're coplanar, but determine a plane means unambiguously communicate this is the one and only plane that we're talking about. Okay, so sometimes, 17, point G and H are in plane X. Okay, so we got a plane X, we got G and an H, okay? What do we got going now? Any point collinear with G and H is in plane X. Oh yeah, that's always true. Okay, and so that's, we have, if we draw this line, if the 2 points are on the plane, well then the entire line is on this plane, right? You're trapped in those 2 dimensions. We're traveling from point G to point H inside that plane. And then we just keep going to infinity, but we're always inside that plane. So that's going to be always true. Notice we're not asked to prove that or justify that yet. That's what, again, the next 3 videos will be about. Okay, 17 says, the intersection of 2 planes can be a point. Wrap your head around that one. So we've got a plane. How could I have a plane like, and these are the drawings I really get as a teacher, right? You get a drawing like this, you go, oh, that's the 1 point, right? And visually, you're like, yeah, I agree. Those 2 things do intersect in a single point. However, those bounds we're drawing for a plane are artificial. These planes are actually boundless, so they expand this way, they expand this way. And what that means is we pierce through this other plane, and the intersection is actually this line, where as we extend this side through and we extend this side through, we get an entire line. The only way that 2 planes can intersect, well, I mean, again, there's multiple versions, but the only way 2 planes really intersect is as a line. The other 2 options are parallel, don't intersect, or they're the same plane, so they intersect in a plane, right? Those are the only 3. So it's parallel, nothing, they touch, and that's at a single line where the 2 meet, or they are the same plane, so everywhere on the plane is intersection. So this is never. Okay, points S, T, and U determine 3 lines. Whoa, that's a good one. S, T, U, whoops, U. That's 3 lines. Yes, for sure that's true. Except, is there any time when they don't determine 3 lines? Yeah, what about the assumption is that they're a triangle? What if we put STU like this? Now S and T make this line. T and U make the same line, S and U make the same line, so they could just determine one line in space. So yeah, I mean, sure, we can name it lots of different ways, but it's only one line in space. So this is sometimes, and it has to just do with whether or not they're collinear. Okay, let's look at 20. Points A and B lie in at least one plane. Yeah, well, I mean, that's, I think, pretty sure that's one of our postulates, right? I don't even know. It's the opposite. If 2 points, oh, here we go. If 2 points lie in a plane, then the entire line containing those. Oh, 2.5, that was the theorem we just used. Yeah, the other ones, we don't have a postulate that says exactly that, but notice that we did use that postulate 2.5 right here, saying if 2 points are on a plane, then the entire line is on a plane. Okay, so points A and B lie in exactly one plane. Well, what do we know about points A and B, right? So if we have points A and B, we know there exists a line, exactly one line that goes through those. Now, how many planes pass through that point? Well, we've talked about that a lot with the idea of 3 collinear points. There's infinitely many planes because there's infinitely many directions that plane could pass through, right? Like you're flipping the pages of a book. There's so many pages of the book at different angles going into that crease. That's the idea. So, yeah, they lie in at least one plane. They lie in infinitely many planes. So, yeah, this is always true. Okay, last one. If line L lies in a plane, and line M lies in a different plane, then lines L and M lie in plane R. What? They never even mention a plane R. Okay, so let's come up with some possibilities. So we've got a plane P here, and a line L, and then we've got a plane Q somewhere else with the line M, okay? Now, do L and M both lie in plane R? So in other words, is there some plane that passes through both of those, right? That's the question. Now, this is a hard one. Let's strip away the planes P and Q and really just think about 2 lines in space. Is there a sheet of paper that you could lay down that passes through both of those? Well, this is a 2-dimensional drawing, so yes, right? There we go. Boom. There's a plane that contains them. So we at least have one example of yes. Now the question is that always going to be true? Or is there one example of no also? Well, here's the one example of no. This is something I mentioned in another video. The idea of 2 lines being skewed. So just take your arms and crisscross them, right? I mean, your arms, unless you did some crazy karate knife move, your arms aren't piercing through one another, right? They're 3-dimensionally in space, and they are not intersecting one arm through the wrist of the other arm coming out. They're different, right? So one is here, and then one passes underneath the other, right? So those lines are skewed. There is no 2-dimensional plane that could pass through this line and then somehow like twist and line up this way in space, right? Like there's no way that you can like twist that piece of paper in space to cut through this top line and then turn 90 degrees and also pass through this line in space. So if you have 2 lines that are skewed in space, no plane can pass through those. So there's at least one example of yes, and there's at least one example of no. I guess I should put an X there. So this one's going to be sometimes true, and that's a really cool one to visualize. So again, 2 lines in space. If they're parallel in space, a plane could go right through them. If they're intersecting in space, then a plane can go through them. But if they're skew in space, no plane can go through those. So this last one, really cool problem. Hopefully you guys are starting to see some of the beauty. I told you earlier on, these are some of my favorite problems, the sometimes, always, never. They really make you challenge yourself to think about the infinitude of all the possibilities. So, okay, I hope you enjoyed that video. Not much factual. I mean, we got, what, 7 postulates, but really cool exploration. I look forward to seeing you guys in the next 3 videos about proofs.